Okay, now we continue to study Chapter 1, Matrices and Systems of Equations. Section 3, Matrix Algebra. Now we learn some algebraic rules. Algebraic rules for any scalars alpha and beta, and for any matrices A, B, and C. We have the first one, A plus B equals B plus A. This means you can change the position for the two matrices when doing matrix addition. And secondly, if you compute A plus B first, then plus C equals A plus, you first do the matrix addition of B and C first. Okay, so you can have these algebraic rules. And thirdly, A times B first, then times C equals A times the multiplication of BC. This means for the left side, you first compute A times B, and for the right-hand side, you first compute the multiplication for the B and C first. Order, it doesn't matter, right? And the fourth rule is A times B plus C equals AB plus AC. And the fifth rule is A plus B times C. You first do the matrix addition, A plus B, and then times C equals, you first do multiplication separately, AC and BC. Then you do the summation, AC plus BC. Okay. The sixth rule is if you have two scalars, alpha and beta, you do the scalar multiplication first, alpha times beta, okay, then times A, which equals alpha times, you first do the matrix, the scalar multiplication beta times A first, so they are equal, okay. And the seventh rule is alpha times AB equals alpha times A first, then times B, plus equals A times alpha beta. So this means the scalar alpha you can put in any position. At first is okay, in the middle also okay, right? And now for the eighth rule is alpha plus beta times A, which equals alpha A plus beta A. This is in fact a distributive property. Okay, and the ninth rule is alpha times this first. This is a matrix addition A plus B equals alpha times A plus alpha times B. Since for the matrix multiplication of three matrices, you can do any two matrix multiplication first. So we may simply omit the parentheses and write A times B times C. Okay, and here we also introduce the exponential notation. If we write as A power k, this one equals A times A times A, k times for matrix multiplication here. You can prove any algebraic rules for these operations. Okay, for example, we prove you first do multiplication of AB first times C, and at the right side hand, you first do the matrix multiplication of B times C. Assume that A is n by n matrix, B is n by r matrix, and C is r by s matrix. So you want to show the left side matrix equals the right side matrix. So it is easy to see that for each side, you will get a matrix. Dimension is n by s. And then you need to prove for each ij entry, they are equal, right? So you can see for the left side is ij entry, so equals the ith row of this multiplication matrix of AB, then times the jth column of C. So the ith row of this matrix A times B, you can write as this one. It again equals ith row of A times for each AB IL equal this one. Okay, and then you can write in this form. You put CLG in this summation. and then you can interchange the position of summations. Okay, after you interchange, you can write here. You first you use L because L only relates to the second and the third term, so you can write here for L, where L varies from 1 to R. So this one is just the ith row of A times the jth column of this multiplication of B times C. So now you show the ij entry of the left side equals the ij entry of the right side. So we show this property. We show this algebraic rule. Okay. Now we see an application. This application is about marital status computation. We know that each year in a certain town, 30% of the married women get divorced. And we also know that 20 of the single women get married for each year. Okay, and now we have 8,000 married and 2,000 single women. The question is that how many married women and how many single women will there be after n years, assuming that the total population of women remains constant. Okay, so we can have this matrix first. So the matrix A equals this one. So what does this mean? If x is 8,000 for the first entry, 2,000 for the second entry. So from the information, we know 8,000 refers to the married women now, and 2,000 represents the single women now. So here, 8,000 is now the married women, right? And 2,000 is the single women. And if you A like this, this means after 1 year, 70% of the married women are also married in the next year, right? Keep unchanged. And for this one, 0.2 means for the single women will become married. And this one means for the married women, 30% will divorce, right? So they will become single. And this one means the single women still keep single, right? So after you have this matrix A, this X, so after 1 year, the number of married and single women should be A times X. So the first entry, still married, times the single becomes married, right? Plus this one. So the second entry means the married women become divorced, so become single, and plus the single women still single after 1 year. So we have this column vector, and the number of married and single women after 2 years should be A times this A times X. So it's just A power 2 times X. You can have 5,000, 5,000. So how many married and single women after n years? So you just write A power n times X. Okay. Another application is about networks and graphs. So a graph is defined to be a set of points called vertices, and a set of unordered pairs of vertices called edges. Okay, given your graph, you first fix the nodes and the vertex and the edges. Adjacency matrix A of the graph is an n by n symmetric matrix defined in this way. So the ij entry of this adjacency matrix equals 1 if vi and vj is an edge of the graph. So vi and vj, these two vertices, they are connected. Okay, and aij equals 0 if there is no edge joining vi and vj. So for example, for this graph, we have altogether 5 vertices and also 5 edges, right? And then the adjacency matrix is like here, the matrix A. So because we don't consider 1, 1 edge, right? We don't consider V1 to V1. So V1 to V2 is 1. So here is 1 to entry is 1. So from V1, we only connect V2. So other entry is 0. Okay. And for example, the second row, consider V2, right? V2 connected with V1, so here is 1. 2, 1 entry is 1. And V2 and V3, we do not have the edge connecting it, so it's 0. And V2 does not connect to V4, so here it's also 0. And we only have a V2, V5. They are connected by an edge, so here 2, 5 entry is 1. Similarly, you can write all the entries of this adjacency matrix A. So one question, after you see this matrix, what's the feature of this matrix? So it is easy to see that this matrix is a symmetric. See, if V1 and V2, they are connected, 1, 2 entry is 1, 2, 1 entry is also 1. See? So the adjacency matrix is a symmetric matrix. Okay, and we have this theorem. If A is an n by n adjacency matrix of a graph, and Aij represents the ij entry of A power k, then Aijk is equal to the number of walks of length k from Vi to Vj. For example, the number of walks of length 3, you can just compute A power 3, A times A times A. So for example, the 1, 2 entry of A power 3 is 2. This means from V1 to V2, the number of walks of length 3 from V1 to V2 is 2. Okay. So you can just see from here. So from V1 to V2, you think about the walks. The walk is just means like a pass something. Okay, so V1, V2, the length is 3, so you can just walk through V1 to V2, V2 to V1, V1 to V2 again. So this is one walk. And you can also use V1 to V2, V2 to V5, V5 to V2 again. Okay, so the number of walks with length 3 from V1 to V2 should be 2. Okay, so we can show this proof by induction, mathematical induction. So first, when k equals 1, the adjacency matrix just represents the number of walks of length 1, right, from Vi to Vj. This is obviously. And then you can assume for k, this theorem holds. And then you show that for k plus 1, this conclusion also holds. Then using mathematical induction, you can show this one.